Hello everybody, welcome back to another CIV E 398 assignment tutorial. In this assignment tutorial, we're going to be covering assignment 6, question number 3, which deals with pipes. And this is kind of a funny one because if we look back to all our previous equations, we always had some sort of tensor usually given to us, whether it be a stress tensor or a strain tensor. But however, in question 3 here, we're not given any tensors, so this will be kind of an interesting one. And question 3 says a cylindrical pressure vessel with an average diameter of 1.6 meters and a wall thickness of 18 millimeters is made up of a material with a Young's modulus of 2.5 GPa and a Poisson's ratio of 0.3. It says a constant pressure P of 2.5 is maintained inside the pressure vessel. Assuming the length of the pressure vessel is 5 meters, determine, and then basically wants 4 different things. However, as we'll see, they're all related to one simple thing in the end. So part A says the increase in length of the pressure vessel. Part B says the increase in diameter of the pressure vessel. And part C says the change in thickness of the pressure vessel wall. So these first 3 questions all have to deal with how are the dimensions of this pipe changing. And finally, part D says the volumetric strain throughout the pressure vessel wall. So again, it has to do with how things are changing when talking about strains. So that's going to be the key here is if we look at these, whenever we're trying to find a change in length, or more specifically also the volumetric strain, we're going to want to find the strains. So if we had the strain tensor for this question, this whole question's a piece of cake. However, as we quickly notice, we're not given the strain tensor, so we have to figure out what exactly do we want to do. So let's think about the question as a whole. In essence, the question wants the expansion or contraction of all the dimensions of the pipe. Well, we know in order to find these changes in lengths, all we need to do is find the strains. So that's a nice happy face because, of course, finding the strains, that seems simple enough. We've done it a million times. However, we're not given any information about the strains in the pipes. Instead, we're given information about the stresses in the pipes and not the strains. So that's a sad face because we can't just go right to the final answer. We have stresses and not strains. We're going to have to do a little bit of work. However, we are happy again because we know that if we know the stresses, we can find the strains in the pipe through the elasticity tensor. So again, we're happy because if we have the stress tensor, we can easily find that strain tensor. And once we have the strain tensor, well, the question will answer itself. But then we're sad again because, of course, we don't have the stress tensor. So the question is, what exactly do we do? From here, we know the general procedure of the question. However, we can't really start it because we don't know that stress tensor. So in order to figure that out, we have to try and figure out, okay, what is the stress tensor when dealing with pipes? Because as we'll see, pipes are a very specific case, and they're actually a very nice case. So there are 2 conditions when dealing with pipes. So as we see in our nice figure here provided by Dr. Sammer, we have 2 conditions. The first of which is the pipe is capped at the ends. And why is this important? Because this constricts the expansion of the pipe. So the first condition is when we have capped ends at the end of the pipe. Condition 2 is when there isn't any capped ends. So the pipe is assumed to be infinitely long, and this allows for that expansion. So if we look back at the question that we're given, we know that we have a pressure vessel. We don't have an infinitely long pipeline. So for us, we have condition number 1. And this is going to be very important because with condition number 1, we can actually find the stress tensor. So for a pipe with capped ends, the stress tensor is given as follows, where we have sigma 11, sigma 22, and the rest are zeros. So it's actually very, very nice. The only question becomes, what is sigma 11? What is sigma 22? Well, they can be found using the general formula. So sigma 11, simply force over area, which gives us that nice long equation. But in the end, it simplifies down to sigma 11 is simply the pressure times the radius divided by 2 times the wall thickness. And secondly, we can find sigma 22 using a similar process, and we find that sigma 22 is the pressure times the radius divided by the wall thickness. So the only real difference is that 2t, or for sigma 22, we just have t. We don't have 2t. But I know a lot of you guys are wondering, well, I can see why there's no shear stresses. But shouldn't there be a stress in the E3 direction, a sigma 33? Well, there is a stress in that direction. However, since this is a very thin-walled pipe, so the diameter is much greater than the wall thickness, sigma 33 is actually quite negligible compared to sigma 11 and sigma 22. It won't play any sort of effect, therefore we can just ignore it. Which is great for us because ignoring something means less work, and I know that you guys are always in favor of less work. So this is great because by the end of this slide, we now know what the stress tensor is. And then we can basically go through that procedure we defined before to answer this question. So if we know the stress tensor, we can now find the strains. How do we do that? Well, we know that this is a nice isotropic linear elastic material, so the following relationship holds true, where I can find my strain vector if I know my elasticity tensor, which I do because it's just a function of V and E, which I'm given, multiplied by our stress vector. And now we know our stress vector comes right from our stress tensor, which we have. We know everything on this right-hand side, therefore we can solve for our strains. The only trick here, just like in question number 2, is we have to keep in mind that when we're considering shear strains, there's a 2 out in front of them. So when we have our strain vector and we're converting it to a strain tensor, we have to keep in mind that there's 2 times the shear strains. However, for this question, it doesn't really apply, but it's something that you should definitely be aware of when we're dealing with these type of questions. And this is great because now we have our shear strains, or I guess just our strain vector. We have all the strains, not just the shear strains. We have all the strains. Now we can answer the question. So with the strain tensor, we can answer the question by saying, okay, well, the change in length can be found by multiplying the original length by the strain in the direction of that length. So if I'm looking at the length of the pipe, well, the change in length of the pipe is simply going to be the original length of the pipe multiplied by the strain in the direction of the length of the pipe. Well, similarly can be found for the diameter, where the change in diameter is simply going to be the original diameter multiplied by the strain in that direction. And of course, the change in the thickness is also going to be the original thickness multiplied by the strain in that direction. So that's going to be a piece of cake because we have those strains. And then the volumetric strain is simply the trace of the strain tensor. So we have our strain tensor. So our volumetric strain is simply going to be epsilon 1,1 plus epsilon 2,2 plus epsilon 3,3. And that's it. That's the question. So not a hard question. The only real trick to it is finding that stress tensor because, again, we're not given it. We have to realize that, okay, we're dealing with a pipe with capped ends. Therefore, the stress tensor is going to be this. After we have the stress tensor, we can find the strain tensor. And with the strain tensor, or I guess all the strains, we can find the change in lengths and the volumetric strain. So easy peasy lemon squeezy. That concludes question number 3. Thank you guys all so much for listening. I will see you guys in question number 4.